vulnerabilities, and 5 of them are related to circuits. And if you drill down, we have under-constrained circuits, so circuits that allow witnesses that are not really what the developer intended. We have non-deterministic circuits, which is very similar. It's just we are writing this. When you're writing a circuit, you are writing this set of polynomial equations that are not linear, and that means they may have multiple solutions, right? So there is the problem of the second and third solution that you have not anticipated. Then you have a bunch of problems with arithmetic overflows, underflows, and mismatching bit lengths, which all boils down to just saying that finite field arithmetic is kind of weird for developers. It's not expected, right? Like if you study computer science, you spend like 5 years learning about how to work with powers of 2. You know everything about powers of 2. Boom, this word is now destroyed. So not only you are not computing, you are just asserting that the solution you computed is correct, but also you are computing in a very unnatural environment. And then the last circuit-related category is assigned but not constrained. Again, very closely connected to under-constrained circuits, but this specifically pertains to the fault of current tooling, which is that it pretends it's programming. So if you look at something like Circom or even Noir, you have this assignment, you have this control flow, you think everything is nice. If you are a normal developer, you would look at it and you thought you did something, right? While you forgot that the witness generation and the actual proving are separate processes. So this is also problematic. At the same time, 17 out of 26 listed vulnerabilities are of these 5 categories. So 17 out of 26 vulnerabilities are problems in circuits. So it is our opinion that this is the problem to fix. But at the same time, it's worth noting that the non-determinism it's not a bug, it's a feature. It's the most powerful design principle that we have when we are actually writing circuits. So as an example that I'm sure you all are familiar with, the principle is you produce values out of thin air and then you assert that they are correct. So for example, to show that some value is less than 8, you produce some 3 x's out of thin air. And then you assert that each of them is a binary number, so it's a 0 or a 1. And then you show that they, so like if you do the binary representation recovery, they recover to n. Even this has deep mathematical content if you stop to think about it, right? Like it's first of all, it's not at all obvious that like, oh, like if those 3 numbers exist, this means that the number has to be less than 8, right? So first of all, why does this exist? Why do these numbers always exist? Why is this a unique set of numbers? Do we need it to be a unique set of numbers, right? And also, half of the vulnerabilities I've seen related to this, someone doing this in full width of the finite field. Now it's meaningless, right? Now you're So when you decompose a number in the full bit width of the field, you get into non-uniqueness. So for example, a value such as 5, it has like the natural binary representation, the 101, but it also has a very large binary representation that overflows when you recover it into the actual number. Okay, so we can't avoid it, so we should prove it. So now I'm going to show you how we can do it, and we are going to be working with Lean4. So I'm assuming not everyone is familiar with it. So Lean4 is, first of all, it's a dependently typed functional programming language, which also functions as a proof assistant. So this means it abuses a deep theorem in theoretical computer science, so-called Curry-Howard isomorphism, where it treats propositions, logical statements, as types, and it treats programs as proofs. So proving with Lean4 is essentially about writing programs that manipulate proofs. So for example, if you think about the function type, which is denoted by an arrow, this is the same as implication, right? So like a function can take an integer and give me another integer, but a function can also take a proof of some proposition and return a proof of another proposition. And if you think about it deeply, this is exactly the meaning of classical logical, constructive logical implication. So we can reason about programs and mathematical structures. Proofs are code. And this is important because this means they are maintainable. We have like best practices for writing those proofs. We can maintain them over long periods of time. And it's also collaborative, so they get checked into Git. There are multiple people working together on proofs for the same theorems, almost like normal software development. And there is a huge corpus of mathematics that's already implemented there. And as a testament to the collaborative nature and the richness of this language, very recently, a large team of mathematicians completed the proof of Fermat's last theorem. Terence Tao was involved in that effort as well. So yeah, this is a very powerful toolkit. So let's start.
One question: Lean 4 is a recent version of Lean, or is it?
Lean 4 is a very recent version, and the reason everyone is talking about Lean 4 and not just Lean is because there was a very major change in the language between version 3 and version 4. So Lean 4 is a completely different language almost to Lean 3.
Follow up to that: is it more recent than the latest OpenAI models? Do they know how to do Lean 4?
It's like 2 years old at this stage.
Okay.
Okay, so we will use the type prop, which stands for proposition, to represent our constraint systems. So what we will be saying is that a constraint system is a proposition, right? Which logically makes sense because it's a statement about some variables being in some relationship. And we will be using continuation passing style to create a sort of composable circuit builder, let's call it. So continuation passing style, that's a very common technique, again, in functional programming. If you have never done this, you can think about it as callbacks. So we can, you can take this, well, okay, this is, you can think about this as a type that will, constraint A is a type that is a function that takes a callback, and it will eventually produce a value of type alpha and pass it to that callback. And in the process, it will also output some assertions that will sort of bolt into that final prop. So this is how we do this. And we talked a lot about producing values out of thin air. In the logical setting, this is just existential quantification. So this is saying, there exists a number that has this property. I'm not saying anything more about it. And we write a small gadget called unconstrained that captures this. So it binds a fresh variable in under an existential quantifier, and then it passes it to the rest of the circuit builder without saying anything more interesting about it. And one more useful helper that you will see why it's useful in a second is assert, which takes a proposition, so another assertion that we want to add, and it just ends it with the result of the continuation. So this is a fancy way of just saying this and this are true. So with these gadgets in hand, we are ready to rewrite our binary representation example. So we have a helper function called unconstrained bit. It produces an unconstrained value of type f, so an unconstrained field element. Then it asserts that this field element is binary, and then it returns it to the continuation. And our binary rep3, so a function that computes binary representation of at most 3 bits, uses 3 unconstrained bits, asserts that they recover to the input value, and returns the collection of those bits. This is kind of ugly, and if you are a functional programmer, this is for you. We have a monad alert. All it says is we can rewrite it to a nicer syntax. So a monad is a very special construct in functional programming that lets us take code that is kind of ugly and has some specific binding properties and rewrite it in much nicer syntax. So this almost resembles normal programming, but don't be fooled by it. You have to remember that this is not actually programming. So for example, our x1, x2, and x3, they don't actually have a value. Those are just 3 variables in the theorem that we are building. Okay, so what can we do with this? One more gadget that we will need is deterministic. And deterministic is a very simple constraint system that takes a constant and just passes it to the continuation, which is to say it doesn't do anything interesting. It doesn't add any additional constraints. It doesn't use unconstrained in any way. It's just a known value that is being injected into the rest of the system. And our first theorem says that binary representation 3 is deterministic. So for all values f, as long as the value of f is less than 8, there exists a representation such that using the gadget binary rep 3 on that input is equivalent to just using that constant instead. And this is a tiny theorem. It's very easy to prove. But proving theorems of this shape already takes care of all the non-determinism that we have in circuits. So as long as for all gadgets in your circuit you prove a theorem of this shape, so saying that it is equivalent to calling a deterministic computation, you don't have to worry about under-constrained circuits, non-deterministic circuits, and assigned but not constraints. It essentially says that all of your assignments are unique at this point. We can also do semantic properties. So before I said that this is not a way to compute binary representations, I said this is a way to check that a number is less than 8. This is also something that we can now prove. Again, a bit more involved this time around, because we have to, when we are actually writing this proof, we have to be very careful that we do not overflow the field arithmetic. But if the field is large enough, this theorem is true. And because Lean is a very rich language that really has huge expressive powers, we can take this further. So this was a toy example, but as a sort of demo of our system, we implemented and verified the semaphore protocol, and we can actually talk about what the protocol is doing. So for example, we have a theorem that says the signaler in any circuit assignment in semaphore is in the Merkle tree. So if you read it carefully, for any values that you would have in your circuit, and under the assumption of collision resistance of the Poseidon hash function, if the semaphore circuit is passing, so like the statement that is encoded by the semaphore circuit, if that's a valid statement, that means that in our Merkle tree at this particular address, we can find the identity commitment, right? So this means there is no unauthorized signaling in this protocol. I will let this dry for a moment so that you can ingest it.
A question for the audience: who was familiar with the existence of this type of proofs? 1, 2, 3, 4, 5. You guys are definitely participating in what's following. Thanks.
Okay, so another example of the same nature, no double signaling. So again, this time around we have two different assignments to the circuit. So we have two sets of variables, one indexed with ones, one indexed with twos. We have now two collision resistance assumptions, because the semaphore protocol uses two different Poseidon hashes. One is like 1 argument, the other is 2 argument. And we have two instances of passing circuits. So like we know that for both assignments, the circuit is passing. And we know that the external nullifiers, so the action identifier, sort of like the vote identifier, is the same. And we know that the identity commitments of the voter are the same, even if they know two different values that recover to the same identity commitment. If the identity commitments are equal, that means the nullifier hashes will be equal, which is to say that if the person running the vote keeps track of nullifier hashes, then there can be no double voting in semaphore. So this is very practical at this point, right? Like we can take an implementation of the protocol and then kind of recover the theorems that are proven about the protocol in the paper that introduced it. So this is even better than writing a paper in a way, right? Because we have a practical implementation and we show that the implementation has certain properties. And this is all very cool, except we don't write circuits in Lean. Unfortunately, I would love to, but this is not what we've what we've collectively chosen as our technology stack. So we have written a compiler that takes GNARC circuits and outputs the equivalent representation in Lean. So you can write your circuits like you normally would, and then you extract them to Lean. You have this representation that you can argue about. If you go to this demo link, this is exactly the implementation of semaphore done in GNARC, exported to Lean, and then proven correct. So the full workflow for this is you write your circuits in GNARC, you use your compiler to emit equivalent Lean definitions. Then you define your theorems, you prove your theorems, and now the most important part, which kind of obviates the need for audits later. You run it in continuous integration. So this is magic, right? Like we are used to testing our code. We can now do our formal verification in CI. On every commit, you are forced to fix your theorems. Or
I need to hand you over the microphone so you can mic drop, right? Yeah, this is good.
That's the issue with these. So yeah, this becomes an everyday part of your circuit development now, and you are always sure that the properties that you request from your circuits are always satisfied. So we've also used it in the wild. First, we tried to show that GNARC's standard library is correct, and it wasn't. They've had a number comparison gadget that used full bit width of binary representations, which happens a lot. It happened to them as well. So that's a practical result that we actually have a CVE to our name because of this work. We also used this to verify WorldCoin's state management circuit. So WorldCoin has a ZK circuit that maintains the set of all the verified scanned humans. Those circuits are now verified. So we have shown that the system can always progress. So you can always find an assignment that will add new users to the tree. And it also shows that there is no circuit level censorship. So if you can always add any identities, right? So that there is no if saying that like if it's Marcin being added, then reject, which for that use case is also important. A few words about further work on this. So first, and this is something that made me smirk when Ben was talking, we need better support for probabilistic reasoning. So a huge part of like modern ZK circuit development is about recursion. It's about using commitments inside circuits, using all of those different primitives. So there is a need for this, and there is not yet an implementation and not even a sketch of an implementation. This is something that just kind of I'm obsessed about, and I want to solve it, but this is coming soon. This is what I am going to be talking about next year. And the more product-related side of it, this is also coming to Nuar. So we will be partnering with the Aztec team to bring this to Nuar. You will be able to write your circuits in Nuar, export to Lean. The rest is the same. Thank you. That's all from me.
Yeah, you're going to keep a microphone, and we're going to have a second one. No, you'll be part of the...
All right, thank you. So about the probabilistic reasoning, that my impression is that the way that we use probabilistic reasoning in SNARKs in particular is sort of very limited to kind of a couple of theorems, like you use sampler challenge and you use, what's it called, the thing that says that if you sample a random point and evaluate a polynomial at that point, then you're likely to have equality of polynomials. It's gone out of my head. So if you prove those sort of small number of theorems, do you need the verification system to directly support probabilistic reasoning? Or is it sufficient to kind of mark your random challenges as a particular type and then just use those theorems?
So this is, I will go back to the semaphore slides
Okay.
to uncover a lie I've made. Yeah, this one is also good. This theorem is technically false, and I have broken the soundness of lean while proving this theorem. Because the way I've stated collision resistance is actually that if the outputs are the same, then the inputs are the same. This is provably untrue, right? Like I can do a counting argument to show this is untrue. So technically, after I've introduced this axiom, all of lean is unsound now. Obviously, you would have to go out of your way to use this. So as long as you don't use this axiom in the wrong way, you are okay. But what I really want here is I want this to say this is true with high probability. That sort of compounds from all the uses of the collision resistance of Poseidon.
Right, and even if you use the random oracle model here, that's not solving the problem, because then you need to model random oracles. Yeah, I get it.
So there's going to be some sort of like constructor saying this is not a real implication, this is a implication that holds with high probability.
Just to understand, is this part doesn't exist in Lean, or is not specified, or is a future work of Lean, or
if I can explain, if I've understood correctly, this is cheating in a sense, because
the cheating part I understood. So
yeah.
what I don't understand is how do you go past it somehow?
You just have to come up with a model that will enable you to capture this kind of behavior.
Which doesn't exist yet, that model.
It doesn't, yes.
That's your next year thing you talked about?
Yeah, I hope so, if I can come up with this. But yeah, that's exactly why Ben was talking about EasyCrypt, for example, right? Like that's why you need it.
So one question about the approach. You were saying we don't want to implement everything in, people don't write Lean, they don't write circuit in Lean, they try to do something else. And so you have this approach of getting basically at the sort of a low representation. Is this better? Okay. Sorry. Getting a sort of a low representation of what they were trying to code, transform it into Lean, and then try to rebuild the semantic of what they were trying to do. So it seems like in the end, people will write their code in something, and you will have to sort of reverse engineer what they meant. So it seems a little bit like you're doubling your work a little bit. So I mean, basically, you have to in the end, people don't write Lean, but they wrote something to write the signal protocol. But eventually, you have to rewrite the whole signal protocol in Lean anyway. So it's kind of, I don't know.
Yeah, exactly. We compile from the...
You get the constraints, but then what people meant with those constraints, like the meaning of the signal protocol, you had to write it in Lean, and then you had to show that the constraints, they do match.
So we actually extract at a higher level. So with our extractors, we don't look at like the R1CS or the Plonkish constraint system. We extract before then, so that we retain abstraction information. So if you have a gadget in your GNARC circuit, we export it as a gadget into Lean. So.
Okay. Then how do you make sure that you, from this more abstract thing, what goes to the prover is actually, I don't know, I'm missing a little bit of the step between where you're extracting and what goes to the prover. Like okay, if you're not taking the R1CS, for example, you're taking something more abstract, then are you going to generate your R1CS from this more abstract thing, or?
Yeah, so that part is trusted, right? So for example, GNARC is a higher level DSL where you have an API object that exposes some abstraction of gates, and you compose those gates. And then GNARC has a compiler that takes this gate description, and then it returns an R1CS. So it's very possible that GNARC has a bug somewhere in that compilation pipeline, okay, and that is just something that is not covered by this system at all.
Okay, thank you.
My question kind of follows on from that. So looking at the melodic representation of a circuit in Lean, that to me looks like something that could be compiled directly to a circuit. Just define a subset of Lean4 as your circuit writing language, which would have a lot of advantages because you can also directly specify the high-level semantics in terms of proofs in Lean. And then, what do you think about the feasibility of sort of an end-to-end proof that that a particular circuit compiler is correct in the sense of sort of maintaining soundness?
Right. So to the first question, it would be possible to write a very nice DSL for circuits in Lean, and this was mostly a business judgment. I just don't believe anyone would like to use it, or I would like to use it. Maybe you would like to use it.
ECC would definitely like to use it.
But then you have then you have lots of people that are more used to Rust or Golang, and they won't be switching to dependency-typed functional languages. So that was a business decision. The second question about the feasibility of proving that compiler correct, I am a bit skeptical at this point, right? Because you get into proving general-purpose Rust or Golang code, and that is not something we've historically done on a large scale. So I'm not sure if.
Ask your question.
You started your presentation from listing bugs, and then I'm curious. So in your approach, so you're essentially proving the absence of these bugs by establishing full correctness of the protocol.
For some definition of correctness, yes.
Yes. But do you think it's more feasible that, for example, regarding under and over constraint bugs, that this could be proved automatically without, that they are weaker?
It could, yeah.
Yeah.
There are approaches. I think Reilabs is doing something automatic where, they actually try to show that you have a unique assignment to your circuit. I'm not sure if it's able to abuse those deeper mathematical properties that guarantee that something is unique. So yeah, I'm not sure if you can always resort to that, but for simple circuits, definitely you can do this automatically.
Yeah, I mean, especially in case of EDSLs, it can come from just compositionality. If you have gates are consistent on themselves, then proving that the bigger circuit is at least bug-free. We are not talking about the correctness here, but at least the bug-free typically is not too complicated. And the proving correctness is much bigger effort and kind of, I would say, maybe outside of scope for many use cases, especially for big circuits.
Yeah. So the thing I like about this approach is that I can talk about things like this as well, right? So I can start from those low-level properties of everything is deterministic or uniquely assigned, and I can build on those theorems to get to actually proving that the protocol makes sense and not just
And also a tiny joke. So are you using any kind of automation in Lean?
I am using kinds of automations, but we don't have anything specific yet.
To make sure that automation doesn't use your inconsistency.
Go ahead.
Hello, thank you for the presentation. It was really insightful. So I have a few follow-up questions. One is, if I get it correctly, you have a transpiler from Gnark to your properties, right, in Lean.
Yep.
While you wrote the transpiler, did it have any bugs, and how severe those bugs were?
It did have some bugs, yeah. They produced code that was not compiling most of the time.
Okay, so no soundness issues though. That some of the properties were mistranslated, so there isn't a bug, so it doesn't compile, but there is an actual error on what you are proving. You are proving not what the code supposed to define.
I mean, in the very early stages, we also had bugs of this nature, right? Okay. But then it. First of all, yes. This is the trusted part. You cannot formally verify everything in all of your pipelines. But with something like this, the more you use the tool, the more you can trust it, right? And I guess it's a philosophical discussion about how far should we go with formal verification altogether, right? It's a good tool to cover some percentage of your problem space, but you will never be 100% sure, right? Like for example, lean is not formally verified, so that it's quite possible that I am proving theorems, but those theorems are not correct, right? Because like lean is a piece of code written in C++ that is not formally verified. So
Yeah. I have one more follow-up question. So my other question was, are there any limitations that basically for some very large, complicated circuits, you cannot prove them, or there are no such limitations in that approach?
So lean is quite slow. When you get to like 2,000 lines in a single definition, it will start choking and be very annoying to work with. So those are not like inherent limitations, but just...
So I guess like circuits that are proving RSA signatures and that kind of things, it's out of scope, at least for the moment.
No, you can, like for example, in the WorldCoin work, we have a verified version of the Ketchak hash function, because if you retain abstraction, then you shouldn't have a single function that is 1,000 lines, right? You have a function that has 30 lines, and then you call it 30 times, and then it works, right? So.
But the Ketchak implementation constraints are also those abstract away, or you actually prove the correctness of all the constraints of the Ketchak function?
No, we prove that the implementation of Ketchak is correct.
Okay. The circuit
level,
implementation.
Yeah, the circuit really specifies the Ketchak hash function.
Okay, thanks.
Go ahead.
Yeah, I am insanely impressed with this work. I think I'm with some other people here who would really love to write circuits in Lean. I can't help but notice that you have like, with your monadic notation, then you have like kind of a natural DSL for doing this. Have you considered then using the monad to compile to the original constraint language so that you can do round trip? Like you can take the output of Gnark, put it into your system, then and then compile it back to the constraint system and compare? I
haven't considered it, but it's definitely something you could do. You would just have to stop instantiating the monad as this particular CPS shape, and you just use a free monad, and then from that free monad you can do pretty much anything. Yeah, it's definitely doable.
Okay, can I go ahead? Rather simple question. You kind of mentioned Veridice. For my protocol, I got Veridice guys to do the verification. Have you actually looked at the tooling and used Lean to verify any of the circuits that's been verified using the Veridice tooling?
I haven't, no.
Okay, thank you.
Okay, we probably have many more questions, but let's talk about them in the context of the verified verifier. Thank you again so much. This was super interesting.
Thank you.